Welcome. Today we integrate in higher dimensions. Integration theory has a long history. It started with the Greek mathematicians, and very important is Bernhard Riemann, who was developing an integral which we use today. Even so, Archimedes already kind of made headways towards that integral. Let's remind you about this. So we have a function of one variable. So this is x, and we integrate on some interval ab. And what we can do is we can choose a large n, and then we can look at the numbers k over n. So these are rational numbers, k over, so let's just take k over n, k plus 1 over n, and so on. So some of these numbers are inside, some of them are not inside the interval. So we have this interval here from a to b. Now we have the function also. Now what we can do is we can evaluate the function at such a point, go up and produce this rectangle here. We have seen that already in the arc length set up. We always take the left side, and what we do is we sum up. So what we do is we sum up, let me just write it as a sum here. K over n is smaller than, let's make smaller than b and smaller, equal than a here. And then we take f of k over n. So we take the function value and then we multiply with 1 over n. 1 over n is the size here of one of these intervals, small intervals, and then we have 1 over n. So that is what we call a Riemann sum. Actually an Archimedes sum, because we take equal spacing. But what happens is we add up all these areas here. So fk over n times 1 over n, k plus 1. So all of these intervals, which are where the left point is inside the interval ab, we take and we add that up. And then we take the limit when n goes to infinity. And this becomes the interval. By definition, this becomes the integral from a to b, f of x dx. Now, this scares everybody. This, I don't know, maybe because it's psychological, but every student is afraid of the sigma sign. I don't know, maybe because it's edgy. And Leibniz had this beautiful round symbol here for that sum. It also signifies a sum, right? We sum up things, but it's a limit. And this 1 over n then becomes the dx. But that doesn't have any, this is just a symbolic way how we write that integral. And this is the Riemann integral. And it means, we have seen that already, area under the curve. That's an interpretation of this as an area under the curve. And what we are going to do is we generalize this now to higher dimensions. Okay, in 2 dimensions we have, instead of intervals, we have regions. So let's just, this is the xy. Let's make a big picture here. This is xy. Let's just take some region here. Can also have holes. So this is a region in now we have also, we call this usually R. And we have also a function given. fxy is a function of 2 variables. Now what we are doing is the same than we have done before. We just take we make a small grid here, and with spacing 1 over n, also here. And then we go over the whole region with this grid. Like when you write on paper, squared paper. And now what we do is we take a point here. Maybe this point here is k over n L over n. So if this point is inside the region, we count it. And what we do is exactly the same definition than before. So what we do is a sum over all points k over n, L over n in R. Then we take the function value k over n, L over n. Now, think about this is actually kind of going into space here, and there's the graph above it, and what we are computing is the volume of a little skyscraper which comes up here, like that, goes up here until the function value f of x, and we multiply with the base area, and the base area is 1 over n squared. So that's this base area here. And the picture is maybe like that. So that is that's the region here. Picture is maybe like that in 3D. So, but let me just first define what we do when n goes to infinity in the same way. We call this the double integral R fxy dx dy. This is sometimes also abbreviated as dA. But that's the double integral, called the double integral. And what it means is it's a volume now, kind of a signed volume. Maybe let me make a picture to show this kind of here. So in this case, what we have is kind of something which looks, I'm not sure whether I can get that down like that, and then something like that, and then there's a little hole here taken out, and so that's the region in the xy plane. So that's x, that's y, and that's c, and now we have the function fxy, which is given above. So that's kind of some kind of graph. I don't know how that looks like, but that's something which is above here. So this is f of x of y. And what we compute is the volume here. So what we compute is a volume. Riemann fell. So, and also Newton got mixed up. Everybody, and that's Archimedes. Also Archimedes got screwed. So what we have here is a volume. So this is the meaning is it's a signed volume under the graph. Signed because it can also become negative, right? If it is below, then it counts negative. Similar than we have in one dimension, right? So this is counting positive and this is counting negative in 1D. That can also happen in 2D. But that's the definition of the two-dimensional integral. And but that's not how we compute it. This is this Riemann sum here. Also, it's also called a Riemann sum. We don't do that, except if we do it numerically. So the Fubini theorem is not only a theorem, it's a whole idea. We want to reduce the integral, a double integral, we want to reduce it to single, to one dimensions. But the square case is really a very important special case, or more generally a rectangle. So this is x, this is y, and our region R is now a rectangle. So that's a rectangle which goes from A to B, and here C to D. So what happens here, let me just write down this Riemann sum here. So the idea was just to take this K over N, and then we have L over N, and then we have a grid point, right? We take this grid point, and we take all these grid points here. So let me just make a point here. We have all these grid points here, which fall into the rectangle. Maybe there's another one, another row here. So maybe this is a 5 times 5. Actually, I didn't want this whole complete square. Why don't we do that? Why don't we just do it with 4? So we have a, just make it a little bit bigger. So these are the grid points here. Now what we can do is we can say the following thing. So this sum we can actually write down like that. We say the sum overall where K over N is smaller than B, smaller or equal than A, and then we write another sum where C smaller than L over N, smaller than D. And then we take the function value f K over N, L over N, and then I take a 1 over N, I take another 1 over N here. So that's exactly the same thing we have written down before, but I split it up. And that's a very important reduction idea. Which comes in here, so that we write the double integral as a nested integral, nested one-dimensional integrals. So let's write this down here. So in this case, that part here, that's actually a Riemann sum, like I started with, a one-dimensional Riemann sum. And so what happens is this, when n goes to infinity, that goes to the integral c to d, and then we have f K over N y dy. Do you see that? This part is fixed, but we sum over the L part, over the second component, and then what we get is now just a function which only depends on K, K over N. So what we actually do here is we have summed up things like that. Think about this as a spreadsheet with numbers in it, function values here, and what we have done, we have grouped it like that, and now it only depends on the row. Now we still have to sum up the rows, and what actually happens is when n goes to infinity, this then becomes an integral too, from A to B, and then we have here x here, then dx. So that's very important. This integral which we have written down before, right? This integral R fxy dx dy, or let's call it dA. We have written it down, split it up as an integral of integrals. So this is an integral, and every function value here is an integral again. So that's very important. Now, who tells you that the spreadsheet you have to add like that, right? That you have first to add up all the rows and then the columns adding up. These are the column sums here. And then add up all these rows, add up all the columns. So we can also take the row sum. We can also do like that. That's the same sum, right? You can do that and then add all these row values. So let's just do that. So we can also write it like that. Sum C smaller than L over N, sum a smaller equal to k over n, so this is equal to d, smaller b, and then we have f k over n, l over n, 1 over n, 1 over n. And now what happens here with this, when n goes to infinity, so we have that this goes to the integral from c to d, f, and then, no, that's not c to d, that's from a to b, right? A to b here. A to b. A to b. And then we have x, and then we have L over n. L over n becomes then y when we take the other integral c to d, and then so this was dx and then dy. So now we have it written down as an integral of integrals with respect to x. So you see that both of these things are actually the same thing here. And that's what Fubini has a name for. It tells us if R is a rectangle, it's only true then the integral, so what we have here on the left hand side, a to b, integral c to d, fxy dy dx is equal to the integral of c to d, integral a to b, fxy, and then dx dy. So that's Fubini's theorem. Okay, here's an example, and I invite you to do it yourself to set it up. For rectangles, it's not so difficult to set it up. So one possibility is that we have in the outer integral, we just integrate from 1 to 4, and the inner integral is then the y integral from 3 to 5. So that's important that you have that matched up. So the outer integral here, that belongs to x here. That's 1 to 4. And the inner integral here, that belongs to y. And then we take the function here, x squared y. And then what we do is we start from the inside and integrate that. If we integrate with respect to y, x is a constant. So that gives us x squared y square half from 3 to 5. And the outer integral remains. So, but we can do that, so y is equal to, y is 25 minus 9 is 16. So that's 1 to 4, and then we have 16 x squared over 2 dx. And now we have no problem here. We have a x cubed third, so that's 16 x cubed 2 times 3 from 1 to 4. 4 times 4 times 4 is 64. 64 minus 1 is 63. So that's 16 times 63 times 2 times 3. And so that's equal to 8 times 21. That's equal to 168. And the same thing could be done the other direction, and it would also work. Let me just do that, and you can wind forward. So we can also do that from 3 to 5, 1 to 4, x squared y dx dy. So let's take the inner integral here. This is x cubed third y 1 to 4. Now x is equal to 4. This is 63. So that's integral from 3 to 5 dy. That's the integral 3 to 5, 63 third y dy. That's 21 here. So this is equal to 63 third y squared half from 3 to 5. And that gives us the 16, the 25 minus 9, 16. So that's also 63 third times 16 over 2. And that's the same thing. That's also 168. So it's the same. So before we continue, let me just tell you about two important type of regions which we can treat in the same way. One integral is like that. So if we have an interval from a to b given, and then we have a function, two functions given. So this is equal to c of x, and then we have an upper function given, which is d of x. So the region is sandwiched between these two. So this is a bottom to top integral. So that's actually, if I write this down, this is the integral from a to b, and then we just integrate here from cx to dx. Then we have fxy dy dx. So that's an important special case here. This is what we call bottom to top integral type 1 for Stewart fans. Stewart is the only one who uses this type 1, type 2. So this is a one possibility, and then we have the other possibility here. The other possibility that we integrate from c to d, so that's x and that's y, and then we integrate from c to d, and then we have a left and a right. So let me just write that down. So this is the a of y, so a function of y, and we have b of y. And the region is sandwiched between this, so that's this region. So let's call this left to right. So because we integrate from left to right, once y is given, we integrate from left to right. And the integral is the same, kind of what we have is integral c to d, same setup, but now we have a to y to b to y, and then we have fxy dx dy. So these are the two basic regions which we can deal with easily. And if the region should be more complicated, we can chop it up into such regions. But let's look at examples. So the core part is looking at examples. Let's look at the first example. We need to make a picture. Very important. Make a picture. Because this is not clear how this region looks like. If you look at this sentence, it doesn't make sense at first. So, but what we have is we have a graph which we know, which is x squared. And then we have also a graph which is x to the fourth. We have looked at that before. X to the fourth is kind of something like that. But then it grows faster, and at some point it will overtake x squared. So that's x to the fourth. You can check that if you take 1/10. This is 1 over 10,000, while this is 1 over 100. So this is much bigger than that. So the region which we are dealing with is this region here. Now, another part of this question asks kind of from where to where do we have to integrate? And if you put that equal, we put an equal, x squared is equal to x to the 4, we see that either x is equal to 0 or x is equal to plus minus 1. So we have here also the region. And now we can, once we have that picture, we can set up the integral. So what we see is that x goes from -1 to 1, -1 to 1 dx. That's how you start with. So you have the outer integral, we write that down. So this is the outer integral from -1 to 1. That's the, and let me just maybe make it blue because that has nothing to do with the lower x to the fourth here. The x to the fourth comes in the inner end. So this is now a bottom to top integral. Best done with bottom to top. And the bottom is the x to the fourth. You see it from the picture. And the top is x squared. And now is another thing. Area, when we compute area, what do we have to do? And actually this is a general fact, a general thing which I should have mentioned before. So the area of a region That's just the integral over the region, and then you have that region, and you just take the function 1, because base area times height is the volume. So we just take 1. So that's a very important case. One always forgets this thing that we can compute area with double integrals, not only volume. This is the height, and this is height times area. So picture is like that, right? If you have a region R here, and then the height is equal to 1, right? So we compute the volume is equal to the area times height. And so in this case, when we integrate 1, that's the area. So in this case, we just integrate 1. The function is just the function 1. And then we have that. Now it's no problem to do that integral. So we take the inner integral here and we integrate with respect to y. So we have the outer integral left, and this is x squared minus x to the 4th. Right, then we integrate 1, we get y. Y evaluated at x squared gives us x squared. Y evaluated at x to the 4th gives us x to the 4th dx. And so that's x to the 3/3 minus x to the 5/5 evaluated from minus 1 to 1. And that's just 1/3 minus 1/5 times 2. So this is 215, this is 415. 4/15. That's the area of this region. So we can learn a lot of this. We had to kind of find the intersection point. We had to make a picture. Very important. And we had to see that the area is actually just when we integrate 1. That's the first example. Okay, in the second example, again, we have a word problem, so we have to make a picture to see what is going on. This doesn't make sense if you just look at it. So we have to kind of imagine what this region looks like. So this is x and this is y. And then we have the curve y is equal to 1 minus x. So that's one curve here. This is 1 minus x, a slope minus 1, so that goes like that. So that's this line here. And then we have y is equal to 1 plus x. Just here, y is equal to 1 plus, slope 1, and also goes through that point here. But now it's slope 1. So this is y is equal to 1 plus x. It actually pays off that you write everything also here, so that you can think with a picture. So this is 1 minus x. And then we have the third region is this region here. The third line is y is equal to 0. That's this one. So now we see the picture. It's just a nice, beautiful triangle R. So, and then we integrate y. That's a function which actually comes up like that. It's a volume of a kind of tetrahedron type region, but we don't care. We think 2D. So that's the important picture. Now here, we could also set it up as a bottom to top integral, but you see what is the difficulty. We would have to go from here, from minus 1 to 0 first, and then take this upper part and then this up. We would have to break it up. So bottom to top is not so good. But left to right is the right thing to do. We take left to right. So left to right integral means we have to kind of see, this is 1 here, we have c to d, right? This interval here goes from 0 to 1, from 0 to 1 dy. So that's the outer integral is now a y integral, right? That's the outer shell. We go from here to here. If we go from 0 to 1, we take this. We go from here to here. And then for every y, for every y, we go from the left to the right. We go from the left to the right. That's why it's called left to the right. We go from the green to the orange part. So what is the left part? We can read it off. We can read off y is equal to 1 plus x, which means x is equal to y minus 1. So it's important that we have now x to put in here. So we have dx, and x goes from y minus 1, that's the left part. And then here also we have to solve this, right? We have to solve this for x. So this is y, this means x is equal to 1 minus y. So that's the orange thing, so 1 minus y. And then we have to fill in the function. So in this case it's not 1, not an area, but in this case the function is just y. I kept it simple also. The function depends also on y, but it could depend on x and y. So this is f of x of y, which we put in here. Note that f of x of y has absolutely nothing to do with the region. So this is a part of the problem, and this is part of the problem. They have nothing to do with each other. The function above, that's something else. So now we are in business to actually do that, and so we integrate that with respect to x, right? And we integrate that with respect to x. We'll keep the outer integral from 0 to 1 dy. But now the x integral, that's constant, so that gives us just x evaluated at 1 minus y is 1 minus y minus y minus 1. So we integrate yx, and then we go, let me just make it slower, 1 minus y, y minus 1. And so that's the inner part here. Just put a little bit more space here. So this is dy. So that's equal to the integral from 0 to 1. Now x is equal to 1 minus y minus y minus 1. So that's 2 times 1 minus y. So let's just write it down a little bit more convenient. So that's 2y minus 2y squared dy. So this is equal to y squared half. So that's y squared minus 2y cubed third, evaluated from 0 to 1. So at 0 it gives 0, at 1 gives 1 minus 2 third. That's 1/3. By the way, what we have computed essentially here, actually exactly, is this point 1/3. That's when you would hold that triangle and balance it. It just has, that's the center of mass. What we have actually computed is the average y value, which gives us the center of mass here. Where do we have to hold that triangle such that it balances exactly? Okay, so in this problem we have just an integral given me, not the region, so it's just an integral. It looks easy, but if we start doing that and try to solve this integral, we have to look up the antiderivative of e to the minus x squared. And the problem is there is no elementary function which gives you this. It's the error function which appears in statistics. This is the Gaussian, essentially the Gaussian density, the bell curve. So there is no elementary function. We are stuck here. So there is no antiderivative. We still can compute that. And the magic is multivariable calculus. We can actually set up this integral and turn it around. That's why we call the order of integration. We can change the order of integration. Let me just make the picture here. So it's important to make the picture. Very important. So we have to make a picture. Without the picture, it's almost impossible to do. So let's read this. It tells us y goes from 0 to 1. So y goes from 0 to 1. That's the outer integral. And then, so this is a left to right integral, because what we have here is we have a function of y which is the left, which is this function here. So this is the left, this is y, this is x equal to y. And then we go up to 1. So that's up to 1. Let's see, that's here. Up to 1 is actually to the right to 1. So this is y is equal to 1. X is equal to 1. So that's the region. The region is a nice triangle. Very nice triangle. So this is what we have here is a left to right integral. Now, why don't we try just to make it a bottom to top integral? So bottom to top integral, we actually have to figure out where this goes. We see that if this is 1 and this is x is equal to y, this goes from 0 to 1, 2. This goes from 0 to 1, 2. But now we have a bottom to top integral, which means we go from the bottom to the top. The bottom is here, 0. That's the bottom. The bottom to the top. Now, in order to get the top, we have to write this as a function of x, right? So this means y is equal to x. Just turn it around. And then we have that. We have to go to x. So we go from the bottom 0, we go up to x. Now, when we do this change of the order of integration, we don't change the function. The e to the minus x squared stays the same. But now we have a dy dx. Now you might think, what the hell? This is the same problem. We have e to the minus x squared. We have still to integrate e to the minus x squared. But that's not true, because we have to integrate with respect to y. This is very easy to integrate. Very easy to integrate, because this is a constant here. So that constant goes out, and then we have y, so that's just x here. So that's actually just x times e to the minus x squared. So we integrate from 0 to 1, x times e to the minus x squared dx. And a miracle has happened. Now we have an integral we have a chance to solve with a substitution, right? We know how to do that when we take u is equal to x squared. So then du is equal to 2x dx. So dx is equal to du half over x. So that's the same thing then when we take x squared. That's the same thing than integrating from 0 to 1 u. So e to the, what do we have? E to the u, e to the minus u half. We just erase this here. I'll write it down here. So that was actually just x times e to the minus x squared. So now we have no problem to do that. And e to the minus u we know how to integrate. So that's e to the minus e to the minus u half evaluated from 0 to 1. So that's 1 minus e to the minus 1 over 2. So we got a concrete answer to this seemingly impossible integration problem. And the key was to really make a picture and change the order. Change the order of integration. That's it for today.